This example shows how gears change the direction of rotation. When the teeth of these two equally sized gears are meshed together, the gears rotate at the same speed, but in opposite directions. Teeth from the clockwise turning gear on the left push down on the teeth of the meshing gear on the right, causing it to turn counterclockwise. These two gears are the same size, but gears can come in all different sizes. The size of a gear can be measured by its number of teeth, by its circumference, its diameter, or its radius. This gear has 12 teeth. If each tooth is 1 inch wide, then the circumference of the gear is 12 inches long. There are other accurate ways to measure the size of a gear. Since we know that the circumference of a circle is pi times the diameter and 2 pi times the radius, the circumference, the diameter, and the radius are all equally good measures of the gear size. When a gear is connected to a power source, like an electric motor or a car engine, it's called the driver gear. The gear to which it's meshed is called the driven gear. In this case, the red 12-tooth gear on the left is the driver gear, and the yellow 24-tooth gear on the right is the driven gear. Because the yellow gear is twice as large as the red gear and has twice as many teeth, it rotates at only half the speed of the 12-tooth driver gear. Since the red driver gear has only half as many teeth as the yellow driven gear, the driver gear must make 2 revolutions to every 1 revolution of the driven gear. If the driver gear is turning at the rate of 10 revolutions per minute, the driven gear will turn at only 5 revolutions per minute. The ratio of the number of revolutions of the driver gear to the number of revolutions of the driven gear is called the gear ratio. Since the 12-tooth red driver gear must rotate twice for every 1 revolution of the 24-tooth yellow driven gear, this represents a 2-to-1 gear ratio. The larger the gear ratio, the slower the driven gear will turn in relation to the driver gear speed. The gear ratio can be changed by changing the size of the gears. In this example, the blue gear with 36 teeth is 3 times larger than the red gear. This gear ratio is 3-to-1. If we want the blue gear to rotate in the same direction as the red gear, we can add an additional gear. Now, this is called a gear train. This gear train consists of 12-tooth, 24-tooth, and 36-tooth gears on 3 axles. As before, the small gear on the left turns twice for each turn of the middle gear, for a 2-to-1 gear ratio. The middle gear turns 1.5 times for each turn of the blue gear on the right, giving a 1.5 gear ratio between the yellow and blue gears. Multiplying the 2 gear ratios together, 2 times 1.5 gives the same 3-to-1 gear ratio as when the red gear meshed directly with the blue gear. So the addition of the yellow gear did not affect the gear ratio, only the direction the blue gear rotates. If direction didn't matter, the yellow gear would be unnecessary. Because gear friction reduces power, engineers never use more gears than are needed. We could get larger gear ratios by adding even larger gears with as many teeth as 48, 6, or even 120. But such large gears can be very cumbersome, and engineers are often limited by space. There's another way of increasing gear ratios, still using reasonable-sized gears by teaming them together in pairs. Here are 2 gear pairs we've seen before. On the left is a 12-tooth driver gear meshed with a 24-tooth driven gear. The gear ratio is 2-to-1. On the right is a 12-tooth driver gear meshed with a 36-tooth driven gear. This gear ratio is 3-to-1. If we lock the 24-tooth driven gear to the 12-tooth driver gear on the right, we create a new gear train. The middle axle now has both a 24-tooth driven gear and a 12-tooth driver gear. This type of gear train, where one or more axles has both a driver and a driven gear, is called a compound gear train. What's the gear ratio for this compound gear train? We can find the gear ratio for the compound gear train by multiplying the ratios of the individual gear pairs together, as we did before. The gear ratio of the gear train is 2 to 1 times 3 to 1, or 6 to 1. We can easily check out our math by counting the rotations of the red driver gear of the first pair on the left and comparing that number with the number of rotations of the blue driven gear of the second pair on the right. Whether you use the mathematical formula of multiplying the ratios of the individual gear pairs or count the revolutions of the first and last gears in the train, the overall gear ratio always comes out the same. The overall gear ratio of this gear train is 6 to 1. Gear ratios are determined by both the number of gears used and a combination of their sizes. In this example, still using only 2 pairs of gears, each with a ratio of 3 to 1, we create a compound gear train with an overall ratio of 9. Using various combinations of 12, 24, and 36-tooth gears, gear ratios of 1.5, 2, 3, or any product of these 3 numbers can be produced by simply adding more pairs of gears to the gear train. In this compound gear train, we have ratios of 2 for the first pair on the left, 3 for the middle pair, and 3 for the pair on the right. The overall ratio for this gear train is 2 times 3 times 3, or 18.